Now that we've discussed the conceptual background for the variance and standard deviation as measures of the total variation in our set of observations, let's turn to our income data again. Our goal here is to obtain an idea of how spread out the income is in the United States. And we're going to use these measures of variance and standard deviation. So let's calculate the variance and standard deviation of this data set. Just to recap, the variance, it's the average of the squared distances or deviations from the mean. Because we're squaring the distances, the variance is always non-negative, so it's going to be positive or zero. The way we calculate the variance, however, it's going to differ slightly depending on whether we have a sample or a population. So when we discussed sort of the conceptual background for the variance and standard deviation, we sort of assumed that we had a population of data, even though we were talking about a sample. But in reality, when you calculate the variance and standard deviation, the formula will differ slightly depending on whether you have a population or a sample. So the variance from a population, meaning if we have the entire population, the variance we call sigma squared. That's just the Greek letter sigma, the lowercase sigma, with a squared term. This is just a reminder that when we talk about population parameters, we use Greek letters. So since we're talking about a population, we try to use Greek letters. So the variance is sigma squared. The variance of a population, you just add up all the squared distances from the population mean and divide by the total size of the population, which we call capital N. So all we're doing is we're taking each observation, we're subtracting out mu, the population mean, we're squaring it for each observation, and we're adding up all these squared deviations or distances, and then we're dividing by the total size of the population N. That'll give us sigma squared. That's the variance from a population. However, when we have a variance from a sample, we calculate it slightly differently and we use a slightly different notation. This is because in statistics, we like to keep track of whether we have a sample of data or a population of data set. So if our data set consists of a sample from a population, the variance we call S squared. We use Latin or Roman letters typically when we talk about a sample. It's calculated in a similar fashion conceptually. So we take the squared distances from the sample mean and we add up all of those together. But instead of dividing by the total sample size n, lowercase n, we divide by lowercase n minus 1. So the variance of a sample, it looks like the same formula for the variance from a population, but instead of dividing by the total sample size, we divide by n minus 1, the total number of observations in our set of data, subtracting out 1. Now, you might ask, why n minus 1 and why not n? Well, this has to do with the fact that we're gathering a sample from a population. So one way to think about this is that in general, sample statistics, as opposed to population parameters, sample statistics, they're calculated based on the number of values that can freely vary in these sets of observations. This sort of number of independent pieces of information, this number of values that can vary freely, that's called the degrees of freedom. So we divide by n minus 1 because that's the degrees of freedom in our sample, which is closely related to sample size, but it's not the same. In general, the degrees of freedom associated with a sample statistic, it's the difference between the sample size n and the number of other sample statistics used in the calculation of the sample statistic of interest. So in this case, the sample statistic of interest is the variance. But to calculate the sample variance, we must use the sample mean. So the sample size is n, and we use one sample mean statistic to calculate the sample variance. So we have a value of n minus 1 for the total number degrees of freedom for the sample mean. So let's just go through this in detail just so it's clear. The sample mean is simply the values of all the observations in our sample divided by the sample size n. So we call the sample mean x bar. We don't use any other sample statistics to calculate the sample mean, so the degrees of freedom is n, the sample size, minus 0. So we have a value of n. For the sample variance, all right, we use the sample mean x bar in the final calculation of the sample variance. So since we're using the sample statistic to calculate the sample, this other sample statistic, the sample variance, the degrees of freedom is n minus 1. Conceptually, you can think of the degrees of freedom associated with a sample statistic. It has to do with constraints. So it's really constraints on the possible values of a set of observations. Suppose we have a small data set that just consists of 3 numbers. And abstractly, we call these x subscript 1, x subscript 2, and x subscript 3. If you're told that you have no constraints, then each number could be anything. That first number could be 1, the second number could be 5, the next number could be 1,000,000. So you have no constraints. If you have no constraints, these values are free to vary. Okay? There are 3 independent pieces of information. But suppose you're told that the sample mean is 3. So you have 1 constraint now. You can freely pick any of those first 2 values, but that remaining value is constrained by the fact that the value of the sample mean is fixed at 3. So suppose you pick the first value as 1, the second value is 3. Since the sample mean is 3, the value of that last observation must be 5. That's because 5 plus 1 plus 3 divided by 3 equals the sample mean 3. So the problem or the issue is that the degrees of freedom is constrained for the sample variance because we already know the sample mean. We use that sample mean, and then it constrains the values of the remaining observations. So the degrees of freedom associated with the sample variance is n minus 1 because that sample mean acts as a constraint on the number of values that can freely vary. To put it another way, it acts as a constraint on the number of independent pieces of information we have when calculating the sample variance. So here's the example written out. It just shows the same sort of discussion that we've just been talking about. So when we talk about sample statistics and population parameters, sample statistics will be based on the degrees of freedom. It's a technical issue, but it is important to keep in mind that the formulas will differ slightly. Conceptually, the population variance and the sample variance, conceptually it's the same. You're taking basically an average measure of variability in a set of observations around the sample mean. So if we return to our income data, we find that the variance is this huge number. Okay, the sample variance, S squared, is this huge number. And we're calculating the sample variance for our income data because it's actually a sample of a population. This sample variance is expressed in thousands of US dollars squared. So we're looking at dollars squared. This is difficult to understand, so that's why we like the standard deviation, because the standard deviation will be expressed in US dollars and not US dollars squared. Just to be clear, when we talk about the standard deviation from a population or sample, it also differs. The formulas look the same. All we're doing is we're taking the square root of the variance. So for population, for population standard deviation, you take the square root of the population variance. For the sample standard deviation, you just take the square root of the sample variance. So for our income data, we want to calculate the sample standard deviation. We use this very easily with statistical software. So if you take the square root of our sample variance, we get this standard deviation of about $55,000. This is in the original units, unlike the sample variance, so it is in US dollars. And when we talked about what the standard deviation variance mean conceptually, the standard deviation gives you an idea of the typical distance of our observations from the sample mean. So on average, you might say that people are different in the United States in terms of income by about $55,000. But how can we interpret this? Certainly it's more interpretable than the variance because the units are in US dollars rather than US dollars squared. But is there anything else we can do to really get an intuitive understanding of what the standard deviation of income means and what the standard deviation means in general? To really aid with interpretation of a standard deviation measure for the variability in a data set, it's useful to compare it to the mean. Because if you recall, the standard deviation is the typical distance from the mean. So we can use the mean to help us understand how spread out our observations are. Right? So suppose we have a mean of $100 and a sample standard deviation of $0, then just off the top of your head, what's the overall spread of the data? How can we characterize the overall spread of the data? If the mean is 100 and the deviation, the sample standard deviation, is 0. Well, in this case, is it none, small, medium, or large? Well, it's going to be none, right? Because there is no, the sample standard deviation is 0, so all the values are going to have a value of 100. So you can see that by using the mean, it can help with the sample standard deviation interpretation. But let's say we have a sample standard deviation of $1 and the sample mean is 100, then how spread out are the data? Well, we can compare the fact that the sample standard deviation is much smaller than the sample mean. So most of the observations are going to be very concentrated about that sample mean. So this amount of variability, the amount of spread around the mean is going to be pretty small if we have a mean of 100 and a standard deviation of 1. Suppose we have a sample mean of 100 and a standard deviation of 5, then how spread out? It's still going to be pretty small. Okay? There's not going to be very much variation around the data set. But suppose our sample mean is 100 and the sample standard deviation is 75. How can we characterize the overall spread or dispersion in the data? Well, in this case, you can say, well, the sample standard deviation is pretty close to the sample mean, so let's say that there's just a medium amount of variability. You can think of, there are quite a few observations around the sample mean, but there is some degree of spread, right? And then finally, consider a mean of 100 and a standard deviation of 10,000. And what's the overall spread of the data? It's going to be large. So what you can see is that we can think about how to interpret the sample standard deviation by comparing it with the sample mean. In each of these cases, we've kept the sample mean the same. We've just altered the sample standard deviation. And if the sample standard deviation is very large relative to the sample mean, that's characterizing a distribution that has a lot of spread around that mean. If the sample standard deviation is really pretty small, relative to the sample mean, then you can say that there's none or a very small amount of variation, meaning a lot of the observations are concentrated around the sample mean. So we can use the mean to help us interpret the standard deviation. In general, if the standard deviation is larger than the mean, this suggests the data are spread out. If the standard deviation is smaller than the mean, this suggests the data are really concentrated around the mean. There's not much variability. So let's look at our income data and try to understand what the standard deviation is telling us. The sample standard deviation is 55,000 US dollars. The mean income is around $37,000. That value for the sample mean is smaller than the value for the sample standard deviation. This suggests that there's a relatively large spread around the mean. To put it another way, we think that based on these values, that there's a certain degree of variability. There's quite a bit of variability in terms of the income of Americans based on this sample data. So now we've talked about measures of center and location, the mean, median, and mode, and percentiles and quartiles. We've also talked about measures of spread or variation. We've talked about the range, the interquartile range, and then we've talked about these two measures of variance and standard deviation. The variance and standard deviation are useful because they incorporate information from all of the observations in our data set and not just, for example, the minimum and maximum values in the case of the range or the third quartile and the first quartile for the interquartile range. So things to know for our discussion of measures of variation or spread for this week. The range is the difference between the maximum and minimum values of a variable. The interquartile range, it's the middle 50% of the data, and it captures the difference between the third quartile and the first quartile. The average of the square distances from the mean we call the variance, and when we take the square root of the variance, we call that the standard deviation. And the formulas differ slightly for the sample standard deviation and the population standard deviation, but conceptually, all you're doing is you're taking the sum of the square distances from the mean, dividing by the total number of observations or degrees of freedom for a sample, and you're taking the square root of that, and that will give you the standard deviation.